Hi, my name is Bao, and I'm with Dang and Wang. And for our project, I'll be presenting our convolutional architecture we trained to enhance the accuracy of brain tumor segmentation. Now, accurately segmenting brain tumors have been a challenge for decades. Manual and traditional practices were often very time-consuming and subjective. The biggest reason for why is the case is because of heterogeneity. What that means is that different tumors such as edema and necrosis can look very different morphologically. They also appear with different intensity patterns across MRI sequences, making it very hard to identify and look for the exact position of the tumors. You can also see from the image here that the boundaries for these tumors are often blurred and vague, making it incredibly hard to tell which is the healthy tissue and which is not. Fortunately, the introduction of UNet has solved this. It follows an encoder and decoder structure where images are compressed to extract features in the encoder, and the decoder reconstructs a segmentation map from the features. There are skip connections between the encoder and decoder layers that helps retain the spatial information of the MRI images. However, it has an issue. The direct skip connection don't always capture the semantic and the spatial features effectively, which results in a more enhanced version of UNet, which is called UNet++, which replaces these direct skip connections with a series of convolutional blocks connected by nested skip pathways. You can see this from the diagram, where the X blocks represent the two convolutional layers, each followed by batch normalization and ReLU, and this better captures the semantic features by allowing data to flow between the encoder and decoder blocks at multiple semantic levels. Yet, UNet++ still struggles with capturing context at different scales. It mainly operates at fixed receptive fields, making it only learn from one zoom level at a time. So, our architecture solves that by introducing ASPP, or True Spatial Pyramid Pooling. By dilating the pixels differently in different convolutional layers, it adds gap between the filter weights and allows the model to capture information from larger regions without pooling or reducing resolution. And for capturing semantic at multiple scale level, we concatenate the feature maps at the end before generating the output. And we run multiple convolutional layers in parallel at different dilation rates, which helps generate feature maps that capture both fine details in little region as well as large context in large regions. And this is the final architecture of our model. And the convolutional layers here are also improved by adding residual connections to allow feature maps to bypass the layers and directly add it back into the output, which prevents vanishing gradient problems in deeper paths. We also introduce additional downsampling collections between intermediate layers. The previous UNet++ only introduces skip connection and upsampling between these, so we add downsampling in these layers as well as to serve the low-level spatial information and overall improve feature flow across multiple depth levels of the network. And since medical segmentation often involves small tumor regions that are easily ignored, we combine dyes and cross entropies for a loss function to address this class imbalance and optimize it with Atom. And the results were incredible. For evaluation, we use Dye's simple coefficient to record how different our segmentation is from the ground truth while considering class imbalance in segmentation. UNet has a Dye score of 0.76, while UNet++ is doing a little better with 0.78, and our implementation with UNet++ and ASPP has a Dye's simple coefficient of 0.848, which is much higher than both of the previous models. So yes, that's it for our presentation, and thank you for watching.